Okay, good afternoon. I am John Davidson, the Deputy for the Flight Mechanics Technical Discipline Team at the NASA Engineering and Safety Center. Today, Dr. John Hansen is giving his presentation entitled Launch Vehicle Design and Requirements Verification Using Statistical Methods. The webinar is being recorded for distribution on the NASA Academy website. I will moderate a question and answer session during and at the end of the talk, so please queue up your questions in the chat feature or use the raise hand icon to ask your questions. John Hansen has been with NASA since 1990 and worked for over 20 years in the flight mechanics and GNC discipline. He was a team lead, branch chief, and technical assistant for the division. He led flight mechanics GNC work for the X-33 and the Ares projects and led the advanced guidance control project that led to the adaptive flight control being used for SLS and developed the process being used for verifying probabilistic SLS requirements. He was the alternate lead systems engineer for SLS from 2011 to 2016, followed by detail assignments as SLS Deputy Chief Engineer, Vehicle Management Division Discipline Lead Engineer, Technical Assistant for the Structures and Environments Division, and Technical Assistant to the SLS Chief Engineer. He worked in the NASA Office of Chief Engineer as the Deputy HEOMD Chief Engineer for Exploration Systems Development and was Lead Systems Engineer for the Exploration Upper Stage. He is currently Deputy Chief Engineer for Systems Engineering and Integration in the Moon to Mars program. He is an AIAA Associate Fellow and has received the AIAA DeFlores Award for Flight Simulation, the Silver Snoopy Award, the NASA Exceptional Achievement Medal, and the NASA Exceptional Service Medal. And he holds a PhD in Aerospace Engineering from the University of Michigan. Let's welcome Dr. Hansen.
All right, thank you. Can you see my cursor? Just a question.
Yes, sir.
Okay, good. All right, I'm going to go ahead into this, and if you have any questions about clarifying what I'm talking about, please feel free to ask them now. If you have a question that might lead us into a different discussion, probably be best to hold those until I finish. So here's what I want to talk about. I'm talking about statistics for launch vehicle design. It's applied to launch vehicles, but for any complex system where you are modeling the behavior of the system and trying to understand what its uncertainties do, you can probably make use of the same procedures. So I think they're pretty generic from that point of view. So this is kind of divided into two sections. The first is when we're doing simulations and we are during the design phases, how do we correctly model our vehicle or our spacecraft concerning what we know at that point in time, how much uncertainty we have, how much uncertainty we're going to have when we actually fly the thing. So separating these different parameters, how much do we know when we're assembling the vehicle, but we don't know it, early in the design phases? How much do we know before we actually launch the thing? How much do we still not know at liftoff? And how do we correctly model all that? And then the second part of this, we'll talk about how many Monte Carlo samples we want based on, we want to prove that we can meet requirements for whatever we're building, and we may want to figure out design parameter values to use during the design, and I'll talk about all those things in more detail. So that's just a preview of the things we'll be talking about. So first of all, the vehicle models. So we estimate these things during the design phases, but we have relatively large uncertainties. We might be developing an engine. We think we know how it's going to perform, but we have a fair amount of uncertainty in that. Then when we build a specific rocket, we will know those parameters a lot better. Maybe we'll put engines on test stands. We might weigh our components and get accurate values for how much each thing weighs. Early in design, you wouldn't know those things. And some things you know better on flight day. For instance, in launching a rocket, you will typically have an estimate of what the flight day winds are, and you can use the known parameters And there's a couple others too that I'll talk about later, but you can use the known parameters to design the flight day trajectory that this rocket's going to take. And then there remains uncertainty on flight day. So there's different kinds of uncertainty here, and I'm going to talk about how we characterize the vehicle correctly in our simulation to model all that. So there's actually 4 types of variations that I'll discuss. First is the uncertainty during the design phases. How do the engines perform? What are the aerodynamic parameters? And as we mature the design, we typically understand these things better, so the uncertainty will decrease. Then about a particular assembled vehicle, we have the weights that I mentioned already. We may have better estimates of performance, like from testing engines, from measuring burn rates of the solid propellant if we've got solids. And we can get that all better. We'll have wind tunnel testing, better information about how much drag the rocket's going to experience, those kinds of things. So that's the second type. So first of all, during design phase. Secondly, for a particular vehicle. And we want to be able to meet our requirements, our performance and whatever requirements we have, and our design limits. How much dynamic pressure is the thing going to feel, how much acceleration, and so on. We want to understand what those could be early in the design phase so that we design everything to be able to meet those things. And so in our simulation, we would figure out what values we want for those, and we would assume those are knowns in the simulation. And then the third kind is things we know about on flight day. So we can design the trajectory to those things, and we can make a go, no-go decision when we actually come to launch. Things like if we have a solid rocket motor, how warm is it? That has an influence on how much thrust and how fast it burns that you get. And then an estimate of how much propellant you actually have on board based on your loading experience and how cold the propellant is and things like that. And an estimate of the winds, like I mentioned. And then there's things you don't know when you launch it. There's remaining uncertainties in all the parameters. You estimate these things, you measure them as best you can on the ground, but you still got uncertainty in all those things. Now, if we threw all this stuff into one Monte Carlo sim, we would not get the right answer for anything. And I'll show you an illustration on this slide here about why that's not the way we want to do it. So about why it's critical to separate the unknowns. So here I've got an example case. On the x-axis is number of standard deviations, and on the y-axis is the probability density. And I'm assuming that that just for the sake of illustration, we have a series of unknowns about the vehicle model that we're representing by this normal distribution here, and then a series of unknowns about the flight day effects. So the red is vehicle effects, the green is flight day effects. And if we just threw them into one Monte Carlo hopper, the mean of this would be 0, and we would get this blue curve, which is just a little bit more uncertainty in the outcome because we have both of these things together in one sim. But actually, that's not the case. When you actually launch this thing, you're going to understand things a whole lot better about that particular vehicle. And on the red curve of the vehicle effects, let's say that I wanted to cover for a 3 sigma vehicle effect. So I get a 3 sigma vehicle model, and that's where this vertical line is over at 3 here. And I center the uncertainty of the flight day effects at that 3 sigma value. So I have a 3 sigma vehicle and I want 3 sigma flight day effects, and that puts me out here at somewhere around 6 in my standard deviations from original. Whereas if I just threw everything into the same hopper, I would get something around 4, 4.5. So I'm not going to get the right numbers out for how everything's going to behave and how bad my worst case is going to be if I just throw it all together. Okay. So what we do is we try to model the different types of vehicle early on based on these uncertainties that will have the types of behavior that we're looking for. So we might want a model of a sluggish vehicle and a model of a sporty vehicle, for example. So this heavy slow vehicle model, that's the sluggish one, might have the worst payload capability, or if you have a fixed payload, it might have the lowest remaining propellant. It might take the longest time to clear the tower on liftoff, so the winds might blow it with the most liftoff drift. You might get the worst plume loads on the launch tower. And in a case where you don't have a lot of ample thrust, the lowest performing case will loft the most when you design its trajectory. That might be the worst case for aborts. If in the case of SLS and Orion might does not have a high thrust on its service module, and it might fall like a rock if you loft a lot and you don't have a lot of energy. So that might be the cases driven by a heavy slow model. A light fast vehicle, on the other hand, might give you the highest acceleration, the highest dynamic pressure, the highest bending loads, because for a given wind and higher dynamic pressure, you'll get increased bending loads, maximum temperatures, things like that. So there's things about the vehicle design that are driven by the sporty case. And there might be some other cases depending on your application. For instance, a booster that is high performance, but a high mass on top of it might be the maximum compression loads. So we want vehicle models that represent our design uncertainties about what vehicle we might actually end up with that represent these kinds of variations. So how do we do that? Well, here's a way that you can do that. This is a procedure that we worked up and implemented and used for the SLS vehicle. So the first thing would be, if I have certain outputs labeled Z here, so that's things like how much payload can I deliver to orbit, or what is my maximum dynamic pressure? So you have a simulation and you can change one of your input parameters, like your thrust or specific impulse or burn rate or whatever, aerodynamic parameters, and you can see how much these output things change with respect to a change in those inputs that you're going to vary. All right, so the X's are the inputs and the Z's are the outputs of the simulation. So you generate things, for example, like the partial of dynamic pressure with respect to burn rate. And what you do is you take the uncertainty portion that you'll know when the vehicle is assembled relative to your best guess right now. So you're trying to find out how much do these things that I don't have very certain now, but I will know them better when I launch a particular vehicle, how much different might that vehicle be? And you can generate the standard deviation for the impact of all those parameters by doing a root sum square of the standard deviations of each of the individual input parameters, like thrust, specific impulse, etc., times the partial of the output parameters with respect to those. So that tells me what the standard deviation is for a given parameter of interest. Then, based on what kind of percentage of cases I want to cover for, I determine that step 2 here, the target value for each of these parameters. So where do I want dynamic pressure to be? Where do I want heat rate to be for this vehicle model? For my light fast model, where do I want these things to be? Assuming that the composite behaves like a Gaussian distribution, the target parameter is going to be just the number of standard deviations times the standard deviation that we just calculated. And so, for example, an n equals 3 would be 99.865%. We typically don't use a number that high because when you put that in the Monte Carlo sim and you generate something else, like I want, when I launch, I want to be able to get 99 point whatever % of the cases to orbit. And I want to succeed with a very high fraction of cases. Typically, we don't do a 3 sigma vehicle and a 3 sigma flight day variation. So we typically pick it like a 90% vehicle model, just to reduce how much conservatism you might get. So now you've got the target values that you want. And what is the vehicle model that gives you those target values? Well, what we do is we want to maximize, the way we do it is to maximize the statistical chance of ending up with that particular vehicle. We have more parameters that we can vary than we do target parameters we're trying to hit. So we've got in the light fast case on the last slide, there were 4 target parameters, and for the heavy slow there were 3. And we have more than that in terms of our unknowns that we're trying to pick. So we do a constrained numerical optimization to get that answer. And so we have constraints to the target values that we want. And it could be these 3 or 4 or whatever your values are. And then we choose the input values to get that. And we maximize the joint probability of these input values from the distributions of them. And those distributions could be anything. They're typically, we typically use normal ones, but they could be uniform or whatever. And when you do that, what you find is that the parameters that really influence the outcome vary more than the other parameters. So if in our case, the solid burn rates typically are one of the big driving parameters. So you will get a bigger variation in that to get your output than, let's say, the drag coefficient. So that's the procedure. And there are some other ways to do that, but that's the one that we developed initially. And then, so now how do you run the Monte Carlo sim with that vehicle model in mind? Now, on a particular launch day, you'll have a wind estimate, a propellant temperature estimate for solid motors. You'll have an estimate, most likely, for how much liquid propellant you have loaded. There'll still be some uncertainty in that. So we define the vehicle model to match our targets. We run a Monte Carlo sim to get the desired percentage of natural environments case that we want to run. So let's say we're launching the sluggish vehicle. Well, typically for us, February is the most stressing case because the temperatures are low, and the winds tend to vary more in the winter than the summer. And so you might say, well, I want to launch in a 95% bad case, which would mean any day in February I would be able to launch this vehicle model with a 95% likelihood. And then we run a Monte Carlo sim for the remaining flight day uncertainties. So that includes the remaining uncertainty on all the parameters that we use to define the model. It includes the remaining environmental uncertainties. We do this for each of our stressing models. And for launch months, we find that some months are more stressing than others. So typically we can neck down to only the ones that are most stressing. And for each mission scenario, you may need to cover more than one design reference mission. You want to show that you meet your requirements, and we'll be talking about that in the second part of this discussion. And then you can determine things from that. For example, the flight performance reserve, which is how much extra propellant we carry to ensure that we get this thing to its destination. When you run all these variations, you can get numbers like that. You can also get design driving values, like what is the max acceleration I need to cover for, what is the highest bending load that I need to cover for, and that kind of thing. And typically there are hundreds of values of interest that we track, all sorts of things down to TVC rates and you name it, about thrust vector control, that is. You name it, about this rocket. I'll pause for just a second if anybody has any questions about what I've covered so far.
Any questions for Dr. Hansen so far?
Okay. All right. I did want to mention one other thing about this part of the discussion, which is that there are a couple of different kinds of uncertainties. There's what's called an aleatory uncertainty, which means that it really varies from flight to flight. Each time we launch, these things are going to be different, and we have uncertainty in that. So the winds will vary. Even if we measure the wind, the variation from the measured wind will vary. Solid burn rate will have an estimate, but it actually will vary from flight to flight, and the uncertainty will vary. And then there's epistemic uncertainty, the other kind, which is that there really is only one approximately single value, but we don't know what it is. So, for example, if we are building rockets that are all pretty much the same in terms of their dimensions and their shapes, then there's a aerodynamic axial coefficient, drag coefficient. It's going to be pretty much one value, but we have uncertainty in what that is. The vehicle models, the vehicle parameters that we separate and we build the vehicle models from, those are mathematically epistemic in the sense that there is a value of these things. We don't know them exactly, but we estimate the single value prior to flight. And so we need to cover for variations in that single value. Mass is also an example of that. There's a value of that we, there's some uncertainty in it, but we can get mass itself pretty accurately, although the propellant mass will vary. But there's other values like aerodynamic moment coefficients, slosh mode frequencies of the propellant, the first vibration mode. These are things that we also estimate prior to flight, but there's uncertainties in all of those. And they are primarily effects to flight control. So if we run this simulation with the other things, they don't impact as much. Things like how much mass you get to orbit or what your maximum dynamic pressure is. That's more influenced by the accelerations. Their effects are highly nonlinear, and so it isn't the case that if you just examine certain bounds, like let's say min and max slosh mode frequency or whatever, or specific values like the 90% vehicle model that we built, that would not be a good thing to do because you can't assume that you've got all the right combinations that could make you unstable. You can't assume that you've got everything covered when you do that. And it isn't feasible to take all the vehicle models and all the possible flight day winds and run Monte Carlo sims for every one of them, where we also vary these flight control impacting things randomly, the moment coefficients, the slosh mode, the vibrational modes. So we do this in a different way, and a reasonable approach seems to be when we're running Monte Carlo runs already with for the previous reasons that we've identified. And if you have all these parameters included and you randomly vary them in those Monte Carlo sims, you will get a lot of samples. And so you can see that is telling you that in general you are pretty well handling that from a flight control standpoint. You can also do sensitivity studies with the individual parameters to see where the system might be sensitive and to ensure that it's robust. And then separately, you're doing flight control stability analysis, and you can have margin on your flight control stability to help cover for that.
Hey, John, we did get a question. here in the chat says, do you ever run into issues using distributions that allow for negative numbers when in reality those quantities can't be negative when measured?
I would say that I can't think off the top of my head of a specific case, but I know that that kind of thing has come up before. And if you're talking about an input distribution with uncertainties, we would make sure that the values that we are randomly choosing are positive if that could not be negative. We try to do the best job that we can to to cover how accurately how things are going to behave, and if certain values are not physically possible, we would make sure that those are not run.
Okay, thank you.
All right, I'm going to move on to the number of Monte Carlo samples, and certainly if you think of other questions, we can come back to those. So now let's talk about requirements and design values. So typically we have a requirement that says we have to achieve something. We have to get a certain payload to orbit. We have to get there with a certain amount of accuracy. We might be going off to the moon or somewhere else, and we need to be able to get meet all the right design parameters from that. So it might say usually there's a likelihood associated with that, and it doesn't make sense to say I've got 100% covered, because there's always 10 sigma outliers that are very unlikely, but we don't design to cover for those kinds of things. So a requirement might say, for example, 99.73%. You have to show that success with a 10% consumer risk. And I'll explain all these terms. So the 99.73, that's kind of a typical number, and that's a two-sided 3 sigma number for a Gaussian distribution is where that percentage comes from. So if you, let's say that you want, some angle of attack, the absolute value of that plus or minus to be within a certain value, then you might use a two-sided distribution. If you're only interested in one end of the distribution, like let's say what's the worst performance, then 99.865 would be the 3 sigma Gaussian number. But these numbers, there's nothing magic about 99.73. It's just typically used because we want a very high likelihood of success. Now, the 10% consumer risk is equivalent to a 90% confidence that we have met the number. So if I run a Monte Carlo sim, I randomly vary my cases, and then I pick a new random seed and run it again, and I keep doing that. If I run a whole bunch of separate Monte Carlo sims, only 10% of them would not meet the requirement and 90% would. That's what that confidence and risk means. You might want to design for a certain percentage worst case. For example, maximum acceleration. Maybe I want to design for the 99.865% high maximum acceleration. So how do you capture a certain percentage value from the Monte Carlo sim with a certain amount of confidence? And the values that we're looking for are among the last few samples in the tails of the data. If we run a couple thousand simulations or something like that, we're going to be in the last 1 to 3 values, the 1 to 3 samples in the tails. And there's random variation in where those tail values are according to the random samples that you selected that led to them. And like I just mentioned, if you ran the sim with a different random seed, you would get a different answer. So fitting a distribution to the data is not generally satisfactory because you're not interested in the main part of the distribution.
My bad.
Is somebody asking a question?
Is it leaked out of paraffin wax?
I'm sorry, I didn't catch your question. I'm not, I didn't hear,
Yeah,
try getting closer to the mic or something.
We got a question here typed in. Have you ever tried to model the edge behavior using a generalized extreme value distribution or one of its component distributions?
We have looked at alternate methods, including that for the, and I don't remember the details. This was a number of years ago, but for the kinds of things that we're looking for with a high reliability that we've caught what we want to find out of this approach seemed to work the best. There's a NASA report that we did, and it discusses that the alternative distribution, extreme value distribution type things in it.
And we've got another, I guess, another related follow-up question. How is the analysis of results typically conducted in Monte Carlo simulations, and what specific correlations or criteria are sought to achieve a successful percentage of simulations?
I'm not sure I understand the question. Whoever asked that one, feel free to speak up.
Hello.
Hello.
Yeah.
Oh yeah, sorry. No, my question was more is when you're analyzing your results from the Monte Carlos, how do you determine if this is like good data? I'm not really super familiar with it. Excuse my ignorance, but just what makes this like, okay, this is actually what we're aiming for and it's good data and it makes sense.
So I'll mention a few things. We do a lot of comparing different simulations. If we're building something that's highly complex, we want to make sure we get it right. So we typically will have, for different reasons, different people doing different simulations, and are they getting the same answers? And when you generate a trajectory in a trajectory generation program, you get numbers for all these things. Do the output variations that you're getting out of this simulation make sense in being, close, but in the right direction and about the right difference from those? I think the techniques that I'll show you are pretty reliable in terms of getting these percentages right. Now you may put numbers in here, the output we're going to get, we may get to a high level of refinement, and I'll mention this later, but it's only as good as all your input modeling. If you have the wrong uncertainties in there about the parameters, or if you are not modeling something to the right level of detail, then you might be getting garbage out the other end and not know it. So we do a lot of comparison simulations. Our simulations, we also try to benchmark against things we have really done that we can compare to. So if we've launched other things, we'll model those things in the same simulation, and is it showing us accurate results? Hope that answers the question.
Yes, it did. Thank you very much.
All right, I want to show an example of why fitting a distribution for these outliers is not so good. So this is, I've got standard deviations on the x-axis here and cumulative distribution on the y-axis. And this particular curve is for change in easterly wind component. So if you had a standard normal distribution, for reference, it's this green curve. And there's lots of data points here, but the actual distribution for this change in wind component has a much longer tail than a normal distribution. So if you said that this 99.73 number, it's almost 3.8 standard deviations out. And the 99.865 number is 4.3 standard deviations out, which is much more than you would get from a normal distribution. So fitting a distribution when you're looking out at the tail is normally not a good approach. So what do we do? Well, what we're going to do instead is we will order the results from the smallest to the largest in whatever parameter we're interested in, and we'll study the statistics of these outlier cases. And this is not a new development, but we're applying it to this application. It's called acceptance sampling in quality engineering. And what we do is this: we look at every sample, every sim that we ran where we randomly varied everything, as a success or a failure. So we run n samples, and there is an actual likelihood of failure, which is the case where you exceed the value that you're interested in, and k is the number of failures observed. So if I have a certain likelihood of failure, then I might see, a certain number of failures when I run a whole bunch of samples. And the binomial distribution for that, the probability distribution, is given by this formula at the upper left here. The probability of that I see k failures, given that p is the actual likelihood of failure and I ran n samples, is n factorial divided by k factorial divided by n minus k factorial times p to the k times 1 minus p to the n minus k. That's the formula for it. So if we look at this and we say, okay, let's take 2,000 samples and look at different failure probabilities, how many failures will we actually see? So in the case where the likelihood of failure is 0.24%, that's the graph on the left, we ran 2,000 samples. Hopefully you can see this on your screen if it's big enough. It looks like we might most likely get 4 or 5 failure cases, but you can get 0 failure cases with that likelihood, and you can get 10 failures in your 2,000 samples. There's just a lower chance that you will get that number of failures. And then as we move across to the right, we go from 0.24% to 0.25% to 0.26% for the actual likelihood of failure. And you can see that it goes from 4 failures being slightly more likely than 5 to about even, to 5 being slightly more likely than 4. But the chance of seeing exactly 5 failures is nearly the same in all those cases. And at the lower right-hand graph, we've got the likelihood of failure per trial, which is the actual likelihood. And then the distribution, the probability distribution is on the y-axis. And that's the probability that given I see 5 failures in 2,000 samples, what is my actual likelihood of failure, P? So you can see that 0.25 is the most likely failure likelihood, which is exactly 5 failures, 0.25. That's 5 failures out of 2,000. But I might actually have a lower likelihood of failure. I might actually have a higher actual likelihood of failure. And if I said, oh, I saw 5, I'll just take 5 divided by 2,000 and say my failure likelihood is 0.25. Well, there's actually more than half of the cases where I would be underestimating the likelihood of failure. You can see that the area under the curve is bigger to the right of the vertical line than to the left. So if I want a certain required success probability and a certain confidence level, how do I determine how many failures to allow? So the left-hand graph here is the same one from the previous page. And on the right-hand graph, we've got the cumulative probability function as a function of the actual failure rate. So if the actual failure rate, the actual failure likelihood is 0 or real close to 0, I basically got 100% chance that I will find success if I say I'm going to accept no more than 5 failures when I run 2,000 samples. If I make that my criteria, and the actual failure likelihood is 0, 0 or so, or just above 0, then I'm 100% going to see that. If I put 0.25, I said, oh, I think the answer is 0.25 because I saw 5 failures in 2,000 samples. Well, it turns out there's a 61% chance that the actual failure rate is worse. Now, if I go out to about 0.47% here, the chance that the actual failure rate is worse has now come down to 10%. So what this says is that if I accepted 5 failures in 2,000 samples, and from that I conclude that the actual failure rate is 0.47, there's only a 10% chance that it's worse than that. So my risk, what's called consumer risk, is 10%. And my confidence that I've captured it, that it's at that value or better, percent. So there's this curve called an operating characteristic, which is basically the same curve that we just showed on the last slide. And in this case, we're looking at a case where we're saying required success is 99.73%. And what we've graphed is the probability of seeing 2 or fewer failures if the actual failure likelihood is as specified on the x-axis. So if you look at the vertical line there, that's at the 0.27% where we've got our requirement set, our 99.73% success. And if the actual failure rate is worse than that, you've actually failed the requirement. So that's to the right of that line. To the left of that line is where the design meets the requirement. It's at that failure rate or better. And your risk is 10%. So the risk is the part where the actual failure rate is higher than 0.27%, but you still got 2 or fewer failures. So that's that small red sliver there. Now, what's called the producer risk is that if you're making a quantity of items and I say to you, well, I will accept what you've sent if only 2 or fewer don't pass my acceptance test. They're actually, the producer is risking 90% that you'll throw away where they actually meet the requirement, but you got more than 2 failures. So that's what's called the producer risk. But if you want to design it so that it's accepted with a higher likelihood, then you've got to design to a better percentage to reduce the producer risk. And that's kind of shown on this plot. A producer could design this particular plot, let me clarify, is for a Monte Carlo run with 7,579 samples, and you're accepting 13 failures in this case. But what it's showing is that the producer has to design to a lower value if the producer wants, when you accept it with only your 10% risk, if the producer does not want to have a whole bunch accepted. So in this case, the producer gets a probability of less than 10% of having it rejected when it's a good product. Okay, but I guess what I'd like to do is focus on our meeting requirements and our setting values, which is the right-hand side of this, where we have a consumer risk number that we're looking at. So, if you can run more samples, that makes the distribution tighter. That's what this slide illustrates. If we ran 2,000 samples and accepted 2 failures, that's that upper left case, and that's what the distribution looks like. If we run 10 times as many samples, 20,000, we can accept 44 failures, and that tightens it up. So there's less uncertainty, you don't have to be quite as conservative, and I'll show why that's the case in a second. And then the bottom one there is 200,000 cases where we accept 509. So each of these three gives us the same 0.27% failure rate. But in order to know that we have good, we have to be more conservative when we run fewer Monte Carlo samples. And down at the bottom there, the number of failures divided by the total number of samples. So 2 over 2,000 is 0.001. And then as you increase the number of samples, you see that that number is going up and it's getting closer to 0.0027, which is the number we're trying to guarantee. So in the case of 2,000 samples, you have to be more conservative in your actual design to make sure that you're going to pass this test, versus if you run a whole bunch of samples, 200,000 samples, you don't have as much conservatism in it.
Hey, John, we got a question. Are these acceptance criteria based on assuming any particular kind of distribution?
They are not. It is only based on assuming that we have successes and failures. And we're looking at the binomial probability of successes and failures, and there's no assumption about the input distribution, that's kind of a little bit counterintuitive, I think. But people think a lot of times, well, if I have more input parameters, that means I'm going to need to run more Monte Carlo samples, and that's not the case. When you do it this way and you look at it in terms of successes and failures, it's a function of the binomial probabilities, and it doesn't matter what your input distributions are or how many of them you've got.
Okay, another question said, in the examples, I see 10% risk. As far as safety decisions, how is 10% related to a target/acceptance rate of success, not failure?
So what the 10% represents is that if I run another Monte Carlo sim with a different random seed to start it off, I'll get a different answer. And about 10% of those, the answer would be worse. So it means that I could actually not quite meet that requirement in 10% of the cases. Now, what am I doing with that answer? If I'm designing a structure, typically I've got a factor of safety on my structural design. Typically, I will have some margin in the structural design. And I'll be designing the structure to ensure that it meets the requirement, which means that it probably is going to exceed the requirement. So the question would be, how much conservatism do you need to capture in order to have enough confidence of success? If you said, I only want 1% consumer risk, you see that in the case of the 2,000 samples, I'd have to go way out to 0.4 or higher, and I'd have to put a lot more conservatism in my design to get to that number. So in a rocket, every pound is really important. So you have to consider, am I over designing it or not? And we'll design a structure and we'll put a factor of safety and margin and all those things in it, and then we typically will go and test the structure, and so we'll find out how tough is it really. Another thing you can do if you want to get that risk down is you can run more samples. But in the cases that we do, typically 2,000 is enough samples to get the uncertainty down to a pretty reasonable level. And it gets to be pretty expensive computationally to run all our cases with all those samples.
And the question is, 10% consumer risk the typical value you use in contracts for real life programs? And follow on, does it make a difference if it's manned, unmanned, $1 million versus multi-billion-dollar program?
So I would say for $1 million program, you probably do not examine things in the design phase to as careful a level as we are doing here. You probably estimate things with some margin and build them without as much analysis when it's a much less expensive program. In terms of flying humans, I would say that we do other things. We don't, when it's a very expensive program that does not have a human on board versus does, that probably doesn't influence this so much as you know, what levels of redundancy we have and what happens if something goes wrong in terms of keeping the crew safe. What kinds of safety features do we have? I think that this procedure allows us to get a very high likelihood of success. You would not go to as much effort if you were building a more of a shoestring kind of thing. Okay, so this slide, there's a table here that talks about how some of these things vary, and so in the left-hand column there's the failure fraction desired. So the first three entries are 98% success, then we've got 99.73, and then we've got 99.865. And different values of consumer risk, most are listed as 10, some at the bottom are 50. Then we got allowable number of failures for these particular cases and the minimum number of Monte Carlo samples that we need to take to get to that success rate. So with a 10% consumer risk in the first three cases, you can see that as I do more samples and allow for more failures, the allowable failure fraction increases. So I don't have to have as much conservatism in my design as I increase the number of samples because I get a higher allowable failure fraction. And that trend, it happens all the way down the page here as you take each case and increase the number of samples. Let's see, I guess so if you want to allow for a higher failure fraction, you have to run a larger number of samples, and that reduces that producer risk. If you want a higher likelihood of success, you can see as we go down the page here, a higher likelihood of success means we need more samples. We need more samples if we want lower consumer risk. You see that 50 versus 10, 50 doesn't need as many samples as 10 does. If the number of samples that we can do is limited by the expense, by the computational time needed, then you have to accept either proving a lower level of success or taking a higher consumer risk, or both. But you would then have a higher producer risk. So you might have to design more conservatism in to make sure that you cover for it. And as I've mentioned before, the number of samples does not depend on the number of input parameters. This works for the generic case. As we add input parameters, we don't have to change this. So if I want to know what is my design value of max dynamic pressure or max acceleration or something like that, what do? I order my samples from lowest to highest. In this case, we're running 2,000 samples on this page. The cases that we call failures are those that exceed the limiting value. That could be orbit insertion error, propellant remaining, roll attitude error, separation clearance. Then there's a wide range of things that you could be studying as a result of this simulation. So how do you determine what the 99.865% with 10% consumer risk maximum dynamic pressure is, or acceleration, or whatever? What we do is we interpolate between the outliers using similar triangles. And so in this graph, N is the number of trials. So I've got 0 up to 3,000 on this graph. And the likelihood percentage is on the y-axis. So 100% is at the top, The red line is 99.865%. And so if I accept 0 failures, the success rate, as I run more samples, that success rate increases when I accept 0 failures. And you see that when we get to 1,705 samples, that's where it crosses 99.865. With 2,880 samples, we can accept 1 failure and still get 99.865. And these are all for 10% consumer risk in this example. So this X value, which is where our, let's say we're running 2,000 samples exactly, and we want to know what is our value of our parameter. Well, we can interpolate between the 1,705 and the 2,880 and go from the k equals 1 value to the k equals 0 value by the same fraction as that that distance between the number of samples. And that shows in the equation at the left here. So along this segment from B to A, the 99.865% with 10% risk value of acceleration is found by interpolating between 0.2000 and 0.1999. The last 2 cases, the 0 failure case and the 1 failure case. And the equation here just shows how you do that. The 1999 value of acceleration, that is the second to last data point, plus the right fraction of the way towards the 2000 value. All right, just a couple more slides here and I'll be done. These results are based on binomial successes and failures. They're not tied to the underlying distribution. I mentioned that already. That makes this pretty useful. It doesn't depend on how many parameters you're varying. It holds for all distributions of the input and output data and for any number of inputs. You do have to be careful because if you run a whole lot of samples and you think that you've got this really well pinned down, it's only as good as all your modeling of how the thing behaves and all your input values and uncertainties. If those are off and you haven't captured enough uncertainty or whatever, you're not going to get the right answer. So summary, we showed methods for separating and analyzing uncertainties that are known when the vehicle is assembled, that are known on flight day, and that are unknown on flight day. And you can model it during the design phases doing that. And then determining how many Monte Carlo samples we need in order to verify probabilistic requirements. We address the level of conservatism versus the number of samples and determine the value of various design parameters. And that's the end of my discussion. Guess we might have a few minutes for questions.
Yes, sir. We do have a couple more in the chat here. So there's a question, have you considered Bayesian methodology to incorporate more knowledge as you progress through the design process?
We have, I would say that, anything that we learn in terms of improving our estimate of what a value is going to be and reducing its uncertainty, we incorporate that directly into this process. So if we start building engines and putting them on test stands and pinning those numbers down a lot better, we incorporate that into the modeling and update what we're doing, and show that we run what we call a design cycle where we update everything with the latest information, and we show that we're still meeting everything. We don't specifically incorporate Bayesian methods, but I think what this allows us to do with updating the models based on our latest data and then running those sims is it allows us to keep this one process and just make updates and show that you're still good.
Okay, thank you. And there was another question from earlier. Are some failures more significant and have a greater need to be avoided?
Yes, that's definitely the case. So yeah, if I have if I have a case where I know that if I miss it, I'm going to kill the crew or lose my mission and not get the James Webb Space Telescope to where it needs to go, then I'm going to make absolutely sure I've got that case covered. And you can do that a number of ways. You could run more Monte Carlo sims. You could have lower consumer risk. Probably what you're more likely to do is say, pinning that Monte Carlo answer down is, kind of like refining that exactly is not really going to help me as much as doing a little bit of extra work to make sure that I've really got that system well characterized, doing more testing on it, or adding a little bit of margin in case I've underestimated some of the inputs and the modeling that I've done into the simulation. But at some point, refining the answer out of the Monte Carlo sim is less important than making sure that you've really got all the things that go into it covered better.
And let's see, I did have a question myself. I think earlier on you mentioned about, avoiding too much conservatism in the Monte Carlos. And I've seen a lot of programs, instead of using like the 3 sigma vehicle variations, 3 sigma day of flight, going to maybe a 2 sigma, or a 2 sigma, 3 sigma. I think you mentioned going 90% on some analysis. Do you have a recommendation of what value you should use to avoid too much conservatism?
I don't think I can give you that answer to apply to everything. Yes, we typically use 90% vehicle models, and then we'll run 3 sigma flight day variations. Because once we launch, if the things that go into that 90% model, you'll know on flight day. And if you found that you had a 97% case when you only really designed to a 90% case, well, you haven't launched it yet. So maybe you swap engines out and use stronger engines or something. That you haven't risked it yet at that point. But once you launch it, it's got to get to where it's going. So we will typically use 3 sigma for that. We tend to use a lot of times in failure cases, we go back to 2 sigma because we think, well, the likelihood of having a failure is low, and assuming that you are convinced that it is, and so the percentage, we reduce the percentage case that we have to cover for because we've already got an unlikely event. So part of it is a question of how many unlikely things you're piling on top of each other.
Okay, and I think we should, I guess, take a few more questions, get a few more minutes here because we got a few people raise their hands. Coulter, Russell, you have a question?
Yes, sir. First, just a comment. John, your work and especially the report applying Monte Carlo simulation to launch vehicle design and requirements analysis has been heavily influential in a lot of my work. And so thank you very much for that and just putting that out there for everyone. My question is kind of doing robust control design. And often we start with designing to a nominal trajectory and then optimizing that nominal trajectory. How do you balance the performance across the Monte Carlo such that you can optimize the Monte Carlo, the performance across all Monte Carlo seeds versus the nominal trajectory? And when is it a good idea to lean towards maybe the median of the Monte Carlo set versus the nominal trajectory performance?
Yeah. So certainly, when we run the Monte Carlo sims, a lot of times there will be a mean that isn't exactly on top of the nominal that you've designed beforehand, and I think there's a lot of value to designing things to that mean. There's a procedure that the flight control folks here use where they run Monte Carlo sims with their flight control parameters, and they actually measure how much margin they have for dispersed cases. So they have a certain amount of control margin for the nominal case, and then they have a reduced but still positive control margin for their dispersed cases. And if you wanted more on that, I could probably get you in touch with the right people.
Sounds good. Thank you for that answer.
Let's see,
Oh, you're
two
welcome.
more questions. We got Joey Hackinson. Sorry if I mispronounced your name.
Nope, that's quite all right. Hey, John. So my question goes back to kind of the light, fast, heavy, slow scenarios that are selected. My question is, for epistemic uncertainties, how do you go about selecting which ones will be captured through different scenarios rather than directly dispersing them? Is there a method that you use, or is it mostly just intuition, familiarity with the system involved?
Yeah, in a lot of cases, it's familiarity with the system. I think that if you've got to have, in order to run these sims at all, you've got to have models of how your vehicle is going to behave as a result of varying the parameters that vary in the inputs. So I've got to be able to simulate how much my different parameters in the simulation change when I change each of the things that can vary in the inputs, whether it's aerodynamics or mass or some kind of performance parameter or whatever. So if I don't have a lot of intuition, I can try tweaking those things and see how much the output changes. And if it doesn't make sense to me, of course, I need to go understand it, make sure that I've got the sim set up right. But one thing that your question makes me recall is, sometimes, for instance, engine folks might look at our output and say, well, yes, but our specific impulse can vary by a lot more than you're using in your light, fast, and heavy, slow model. And our answer is yes, but there are other parameters that are varying to make that heavy, slow, light, fast model, and we're getting the overall effect we want. We're not varying any particular parameter by a set amount corresponding to a certain number of sigmas. You could certainly run a case like that, but that isn't part of this statistical approach. And this approach gets you the level of case you want for targeting the output parameters.
Great, thank you.
Okay. And then I guess we'll take one more from Sean Kenny.
Hey, hi, John. I had a question early on in your talk. I think it was like slide 12 or so. You talked about promoting epistemic uncertainties to aleatory uncertainties. There was some mean square thing I believe you were trying to compute there. I was just wondering, have you ever looked at the impact of making that assumption? Seems to me as though you're kind of imparting a degree of precision into the problem that doesn't support the definitions of the uncertainties.
Are you talking about this slide?
Yes.
Okay, so what? And I'm gonna try to explain where this is coming from, and then tell me if that answers your question. So what this is for is there are things that we don't really have a good handle on right now because we're in design phases, but we'll know them a lot better when we get closer to flying. So it's kind of saying when we actually go fly this thing, how well will we know this parameter? And so we divide it up into how much uncertainty we think we'll still have on flight day, and how much of that uncertainty we think we're going to suss out between now and flight day. So this is trying to come up with a statistical case that represents the variations in those things that we don't know very well now, but we will know a lot better before we fly.
Okay, so that's primarily used in the very early stages of looking at uncertainty. Is that right?
Yeah, well, and then even after, let's say we start running tests and things, there are still, for instance, you've got winter versus summer, different kind of behaviors. You still have, I'm building a number of different copies let's say, of this launch vehicle, and each one's going to be a little bit different in its behavior. And but I'm going to measure things about the specific one. So, for example, I might put all my engines on a test stand. And so I'll know for this rocket, here's what the test stand measurements say for those engines that are on that particular rocket. Because I want to make sure the engines are going to work. So I fire them up, then I go put them on the rocket, and I know their parameters better. And the ones I measure for a different case of launching this rocket will be different. So there's not as much uncertainty as there was early in the program, but there still is some uncertainty on vehicle to vehicle variations, even after I've started manufacturing these things and I have a lot better handle on them. So the heavy, slow, and light, fast gets a lot tighter when you get later in the program, but you can still have a heavy, slow, light, fast case. Now, when you get to flight day, you've got your best estimates of exactly what that vehicle is going to do. So it's the actual case. And then you've got what are the things that can vary still. Does that answer your question?
Yeah, that's good. I kind of a follow on though. So getting back to epistemic uncertainties, are they ever utilized in the binomial success failure approach that you presented near the end of your talk? And if so, how do you integrate epistemic uncertainties into that framework?
So a partial answer maybe to that is when we fly, we try to measure as best we can things about the flight that will help us better estimate the actual value of those epistemic cases, so that when we go to our next flight or our next flight after that or whatever, we have better estimates of what those parameters actually are and smaller uncertainties. When we run the flight day simulation and we have an uncertainty distribution for each of the parameters, I think at that point we're not differentiating between epistemic and aleatory. We're just saying we've got an uncertainty distribution for each of these parameters, and then we're looking at the behavior of the output parameters of interest, based on the binomial thing of successes and failures.
Okay, thank you.
You're welcome.
Okay, thanks. I think that's all the time we have for today. Dr. Hansen, thank you very much for giving us your talk today. If anybody has any follow-up questions, you can follow up with Dr. Hansen offline. And also, if you'd like to download the webcast or a copy of the slides, you can just click on the links that are provided in the chat. Okay, well, thanks, everybody.
All right, thank you, everyone.
Okay, bye-bye. Thanks, John.